Okay, good morning. So my name is Shai. And in a few weeks from the beginning of the semester, Asaf taught you everything you need to know about supervised learning, convolutional neural networks, and optimization. And today, if Asaf was teaching you how things should look, we'll dive into the details of what is actually meaning to train a neural network. All the gory details that actually makes the difference between nice theory and nice slides and things that actually work in practice. And there's a lot of small details we need to know when we come to train neural networks. So we're going to touch upon stochastic gradient descent, about all of its aspects, variance, and how it actually works. And then we'll expand on some other topics that relates to how to make the model that we train work in practice. So the pillar of deep learning and machine learning is optimization. So we have an hypothesis class, the functions we are trying to find, the neural network, and it's a family of a function that is parameterized by theta, the parameters. And the key aspect is to find these...
אני לא יודע אם שומעים אותי, אבל לא שומעים.
לא שומעים, רגע. אוקיי, שומעים אותך?
אני שומע.
שומעים, אז נראה לי הכל בסדר.
כן, רגע, שוב בדיקה בזום, שומעים אותי?
עכשיו שומעים.
עכשיו שומעים, אוקיי, בסדר, מצוין, אני אשתדל לדבר יותר חזק, יכול להיות שכשאני זז אולי המיקרופון יתפחות. אוקיי, so just a second, if we made this pause then... Okay. So, as I was saying, in deep neural network, in machine learning, we have a family of functions. And the key aspect is to find one instance, a set of parameters that defines a single function that actually minimizes the loss function, which is the objective function we try to find. So we can design a very fancy neural network. We can design very fancy layers with all kinds of functionalities. But if we cannot find good parameters, if we cannot solve this optimization problem, then everything is in vain. So it's key that we will be able to optimize to find these parameters. So what have we learned about optimization so far? So we took all the objective function, the sum over all the training samples we have, and since it's very computationally heavy to compute it every time, we break it into small batches, and we have a stochastic gradient descent. So we have a stochastic estimate of the gradient that we estimate by a batch, and we learn how to do this in a very efficient manner. So we can compute the loss in our neural network for a batch of samples in the forward pass, and we can very efficiently compute the derivative of the loss in a backward pass. So a single forward-backward pass would give us a loss and will give us the derivative with respect to all the parameters in the model. And once we have the gradients, we have the update rule. So the parameters of the next step would be the gradients time a learning rate, time a step. So is it enough, this forward-backward pass, to find good parameters? Well, now comes the details. So let's talk about this learning rate, this step that we are making. So in vanilla stochastic gradient descent, this is the update rule. We update the parameters, the current estimate we have, with the gradient and we make a small step. And how do we make this step size? So let's look at this two-dimensional loss space. Suppose we have only two parameters, and we can think about the loss over these parameters as this surface. And we start from this tiny point. This is our initial guess for parameters, and we want to make to find the optimal point, which would be the lowest loss. We want to get to the bottom of this pit. So we try with some step size. And since we want to make the optimization process not too long, we'll make big strides. And we are walking in the right direction. But what happens then when we reach here the boson of attraction? What happens then?
The step size is too large.
The step is very large, and we are very close to the optimal point, but we don't stop. We just bounce back and forth because we have very large steps. So maybe we want to make a smallest, make small steps. We want to be very cautious. So if we make very small steps, we don't get anywhere. So we are in the right direction, but it will take forever to optimize this function. So if someone would tell us what is the ideal learning rate, then we would be heading the right direction. And when we get there, we won't diverge. We get to the bottom of the pit. And if we hit the bottom with the proper learning rate, with a very low one, we will stay there. We won't bounce around. So we are very sensitive to this step size. If we set it too high, we'll bounce around. If we set it too low, we'll never get there. And we can think about this stochastic gradient descent as a hiker that is going down the mountain and is only sensitive to its very local ground, what he sees under his feet, and is walking in the direction of the slope. But this is very sensitive because we only have the information that is very local to us. Can we do better? Can we do something that is less sensitive to the learning rate, to the step size? So if we work with analogies, and we don't want to be hikers, there's another way of reaching from the top of the mountain to the valley. We can roll a ball. And a ball doesn't make discrete steps every time it rolls. It has some momentum. It has some memory of the path it got. It doesn't bounce back and forth by every tiny stone that it hits on the way. So now we have this momentum, and we update the momentum using the gradient. So we have a memory of the direction of past steps, and we use this direction, this momentum, to smooth the path. And as you can see here, we bounce around, but since we have a memory of where we are, eventually, like a ball, we hit the bottom of the pit. Okay, so one would argue that, okay, in the vanilla step, we had only one step size, one parameter to tune. Now we have two. We have this momentum, how we want to measure this memory to take it into account. But now that we have momentum, we are less sensitive to the setting of these parameters. So usually the momentum is set to 0.9, if I'm not mistaken, and you can play with the learning rate, but it's quite robust. And we can think about it as rolling a ball down the hill. Any questions so far? Great. So if we're taking momentum, which is the first moment of the gradients, we can think about considering the second moment. We can think about the variance. And this is another version of stochastic gradient descent. It is called Adam optimizer. And again, we are making steps based on the gradients. But now we have the momentum that we saw before that accumulates the gradients. But we also take the second moment of the gradients. So for each parameter, we save in memory how it changed in the past, but also how it varied in the past. So if there is a parameter in our model that keeps changing all the time, so some example thinks it should be positive, some other example thinks it should be negative, it always varies. So we want to make very small steps in that direction because there's a lot of variance. On the other hand, there's another parameter that is rarely updated. The variance there is very low. But suddenly we have an example that will strongly benefit from this parameter. Then we would like to update, make a large step on this direction because we didn't see it coming in the previous. So we keep track of the moment and the second moment of the variance. And the step size for each parameter is modified by the variance. So you can think about Adam as tuning the learning rate, tuning the steps for each and every one of the parameters based on its variance. So instead of having a fixed learning rate for all the parameters, making the same steps in all the directions, Adam optimizer allows us to effectively take a different step in every parameter. So we have the first moment like SDD, we have the second moment, the variance, and there's update, it's been accumulated, so to have an unbiased estimates. And as we said, we weight the change by the variance. So actually, we adapt the learning rate for each of one of the parameters. Yes.
Can you explain again why the second momentum, what we gain from looking at the second momentum?
So we have a variance.
Yeah.
We have, so some of the parameters are changing very frequently. So we don't want to make large steps there because there's a lot of uncertainty. Other parameters are not affecting the model very often. Only very rare examples in the training set are affected by these parameters. Then when we hit this kind of example, we want to take advantage of this and make a large step. So the example we showed, so if we look at this loss function, so the loss function behaves relatively the same in both axes. So the variance here is the same, and it took me a while to tune the parameters here, the starting point, so you actually see that the Adam optimizer actually does something. But if you think about it, if the loss function is scaled differently in the axis, so you have one axis, so this is θ1 and this is θ2, and it is scaled like this. So in this θ1, there's a very gradual change, but on this axis, very fast. So if we try to fit one step size for these two parameters, it will be very difficult. So we make either very small steps in this direction, or we zigzag in this one. But if we weight the learning rate by the variance, and it's adaptive, we don't have to know it in advance, then it will have small learning rate in this direction and larger in this one, and will be converging to the local minimum faster and more robust. Okay, yes.
I'm guessing all of these are good in some situations and bad in some others. How do we know which ones we're supposed to use? Or
so yes. So it depends what you're trying to do. So if my personal preference is to use the most naive way, stochastic gradient descent with moment, just to show that the system I'm working on is robust. But if you are competing on a challenge and you need to get this extra 1% performance, then you need to push hard with all these tricks, and they will give you the extra mileage. So it depends. So if you are in the stage of proof of concept, you want to prove that your model is robust, your model actually does something, it's not sensitive, not too sensitive, work without. Again, if you think that the model that you build has have different components, that each of one of them might have very different variants, Adam is your friend. If you think that all your layers behave roughly the same. So this is kind of consideration. Again, if you download someone else's code and he uses Adam, you probably stick with that. But yes, so finding the right optimizer can give you the extra mileage, but depending on the context, you don't always want to go into this. Yeah.
In the WIS side, I don't find beta 1 and beta 2.
So beta 1 and beta 2 are, you set them. It's like the learning rate, it's like the step size. But again, since the purpose of this is making you less sensitive to the setting of them, you usually use the default ones. So I think you only play with beta 1, which is the learning rate, and then beta 2 is set to 0.99, something like that. And that's the fun of it. So you have more parameters to tune, and it looks like it's more confusing, but actually you're less sensitive. So if you work only with the vanilla stochastic gradient descent, you need to try several values of learning rate, and they will make huge impact. So for some learning rates, the model will not converge. For others, it will diverge. And then you need to find so it's very tedious. Then once you have momentum, you're less sensitive. Okay, so stochastic gradient, momentum, and Adam are not the only update optimizers for stochastic gradient descent. There are quite a bunch of you. Sparse variants and all kind of them. If you have the slides, go to the link and you'll find. But these are, I think, mainstream, what you see in most cases. And as you've asked, the question is, do we really want to converge fast? Does it always does good for us? So let's think about this one-dimensional loss function. And where do we want to be?
Second bit.
This one.
Yeah.
Yeah, it's lower. It's the loss is lower. Apparently, this is where we want to be. It's hard to get there because it's very narrow. But this is the loss function that we have in our hand. This is a loss function derived from the training set. But at test time, we will see other examples. And they won't be identical. And in many cases, there is a slight discrepancy between the training distribution and the test distribution. There is some small changes. So if this is the train loss, the test loss, the validation loss might be slightly different. And now what happens if we converge to this point? What would be the test loss in this case? It would be slightly higher than what we've had we converged to this other minimum. So we don't always want to find the global optimum if it's not robust. Sometimes we want to find these large basins of attractions, even if they are not the global optimum, because they are the solution there, the function that we found, generalizes better. It is more robust to changes in the distribution between the training loss and the validation loss. So if you want to find these robust solutions, we might not use Adam optimizers or fancy optimizers like that. We want to still use the stochastic gradient descent, the vanilla version of it. But again, we saw that it's hard to make it converge. So if we circle back and we want to make the vanilla version converge and not diverge, and we saw that it's good to start with large steps with high learning rate, because then it allows us to get to the region that we want quite fast, but then it bounces back and forth. So what can we do? So we see that we have stages in the optimization. So the first stage, we just want to run around and see like the rough layout of the land. Where should we focus our attention? And then when we hit like the circa of the point that we want, then we want to be more cautious. So what we can do is we can change the learning rate through the training process. So we start with large steps. And then, as you see, the color changes, we decrease the step size. So we start with very large steps bouncing around, but eventually we will reach some interesting area, and then we decrease the step size and we converge to the local minimum that we want. And there's many ways we can think about decaying the learning rate. So we can think of the learning rate over time. So we can use these two steps. We start with high learning rate to search around, and then we decay it. We can have many steps. We can have like a continuous decay. And if you go to PyTorch, you see learning rate schedulers. You see a bunch of functions there, and you can write your own one. Some people use warm up. So you start with very low, increase the learning rate, then decrease. So it's up to you.
Will this rely on getting the timing right, since you start making it shorter? So if you wait it short before you get to the basin of attraction, it's kind of annoying.
Yes.
A lot of time.
Yes, it's so you end up writing a nice code for your neural network, chaining all the layers you want, and then you spend days which optimizer, which learning rate, what scheduler should I use. And as I said before, it depends on what you're trying to get. So if you only want to show that the architecture you came up with is robust, then no fancy games. So maybe just this simple decay, and that's it. And if you're in a competition and you really try to squeeze hard, then yes, you spend time playing with these hyperparameters of the training process.
Okay. There's something I don't understand. The learning rate is decay automatically, like dynamically with the atom.
So no, so all the other optimizers I showed you, they have their own learning rate and momentum parameters. And what I showed you in there, they are fixed. On top of that, you can externally decide that you want to decrease the learning rate.
Yes, after several epochs.
Exactly.
So, and the combination of both of them, like the Adam and the...
So Adam has this momentum that actually scales the learning rate, the step size for each and one of the parameters based on the variance. But again, but still it has these beta 1 and beta 2. these parameters that actually determines the step size. And you can think about, okay, I know the variance for this one, but I want to make the step size for all the parameters, scale it to a smaller one. So you decrease the learning rate. And then for the variables that change, that has low variance, you make a smaller step size, but it's still bigger because the variance is low. And for this one, it's even smaller because the variance is high. Yep.
From the technical point of view, do you have to, like, for the scheduler of the learning rate, say after each epochs decrease and then, or can you say when you begin overfitting decrease, or when the loss begins oscillating decrease the learning rate?
So you implement. So
yeah, but without learning from scratch.
Out of the box, I think there is one scheduler that takes into account the validation loss, but you need to provide it to the function that computes the learning rate. But you control it, so you can write your own scheduler. It's not very difficult. But I don't think we're going to do this in our exercises or in the project. But yeah.
Maybe I'm taking us a little bit backward, but can you explain how do you see the concept of different step size in each variable or in each direction in the Adams formula?
Yeah, these formulas are difficult to take in, but you see the second moment here, which is updated by the square of the gradient. So actually it accumulates the variance. And then we divide by the square root of the moment, by the second moment, the variance, for each and every one of the variables. So think about it. When you train a model, you have a vector theta of all the parameters stored in the model. And then the optimizer has to store the moments for all the parameters. And in Adam Optimizer, you have a second copy which stores the variance for all of them. So if you have 1 megabyte of parameters in your models, then actually using Adam, you'll use 3 megabytes in memory because you need 2 more parameters for each parameter for the optimization. And this is like element by element division. So theta I, the ith parameter in t+1 is the theta I at t times the moment that we computed by the gradients divided by the so this is the first moment divided by the variance. And this is how you control this scaling. And it's done for each parameter.
Shai, is there a demand for beta 1 and beta 2 to be much smaller than 1? Or?
On the contrary, they are very close to 1. It's 0.999, I think, for beta 2, and beta 1 is 0.95 or 0.9, something like that.
Okay, but they cannot be above 1 because otherwise it's going to be like change of sign.
Yes, something weird would happen. I never tried this, but yeah.
Okay, thank you.
I think the whole point of using this kind of optimizer is that you rarely play with the default parameters. Great. So we're doing stochastic gradient descent. Do we have any guarantee on the convergence of our process, of our optimization? Do we have any assurance that we'll reach the global optimum? And so, as I see you noting, no, we have no guarantee. The loss function is very non-convex. There are many local minimas. And once we are inside this basin of attraction, and we are only making small steps, even if we have momentum and variance and whatever, we are only making local consideration. At no point do we have like the global picture of how the loss function looks. We always have a very local estimate, so we have no guarantee. Is this a bad thing?
Yes.
What?
Why not?
Why isn't it a bad thing? We don't have guarantee, it's not optimal, but let's think about what is the geography, what is this landscape looks like. So let's look at this very small example. So we have 2 input variables, and we have 5 hidden neurons. So it's a 1-layer neural network. So 1 from the input and 1 from the out. So 1 hidden layer and 1 output layer. Okay. So 2 layers. And we can write the function that this neural network implements as this. So the output is a weighted sum of the 2 inputs, time a non-local activation, weights for the output layer, and the output. And just as an exercise, how many parameters do we have here? We don't have biases, just linear weights.
5 choose 2 plus 5 choose 1.
It's not choose, it's just times. So we have from 2 to 5, we have 10 parameters for the first layer, and then from 5 to 1, we have additional 5. So it's a 15-dimensional vector of parameters.
And bias.
Let's ignore the biases. So 15 parameters, it's a bias-free network.
Just confusion. You said non-local activation function. Is it non-linear or?
Yeah. So the local the sigma, we have a non-local, but think of ReLU. There's no parameters for the actual non-local activation. The parameters are only in these linear combinations.
So what do you mean by non-local?
So we have a linear operation W1, the matrix of weights, which is 2 by 5 times x. And then element-wise, we apply a non-local function, like the ReLU function.
Non-local is like non-linear.
Non-linear, sorry.
Okay.
Okay, non-linear, sorry. My bad. I'm making slides for another talk. Okay, so the nonlinear function, and again we have another set of weights for the second layer and another nonlinear activation. Sorry, nonlinear. So we have a 15-dimensional space. So every point in this space is a different instantiation of this network. It will give us different loss function. But are all the points in this space different from each other? So do we have different solutions? Not exactly. Think about what happens if we just shuffle the neurons here, if we permute them. So we add a permutation matrix that changes the order of the neurons, but it doesn't really change the function that we compute. So we take the input, we route the weights slightly different, but it's the same function that we compute. These two permutation cancels out. So we have exactly the same function, but it's a different point in the space of the parameters. So we have these copies of the function in different space, in different areas of this high-dimensional space. And you can think about it that the space looks like karton beitzim. I don't know how to say it in English.
Egg crate.
Egg?
Crate.
Egg crate. Okay, thank you. So now it's highly non-convex, and we can reach different local minimas in this space, but each and every one of them is actually the same as the others. Okay, so no, we have no guarantee about getting the global minimum, but every minimum that we find is not unique, and it's the same, it's equivalent. We don't care about any specific copy of these parameters. Another thing to take into account is that a local minimum is a point that in every one of the directions that you try to move, you're going upwards in the loss. So this is very strict when you are in 1D or in 2D, but when you are in 15 dimensions, the chances that you reach a point that in every one of these 15 directions you're strictly going up is more difficult if you are far away from the global optimum. This is 15 dimension. If you are in 1,000,000 dimensions, it's even more difficult to find like a very robust and stable local minimum that it's very difficult to escape from, and you are far away from the global optimum. So there's no guarantee, there are no theoretical guarantees on this stochastic gradient descent process. But in practice, since we're working in these very high dimensional spaces, the points that we converge to usually are not that bad. Okay? So we are doing this stochastic gradient descent. We are going in the direction of the slope, but we need to start somewhere. Where do we start? How do we initialize the weights? So we build this fancy neural network, we decided on the layers, but we need to set some numbers for the parameters. We need to start somewhere. So what if we initialize everything to 0 because we don't know anything a priori, we don't want to assume anything? So we'll start with 0 and we'll see where it gets us. What will happen then? Yes, if we recall correctly, we work with linear layers, and the gradients with respect to the weights are the derivative with respect to the inputs, and everything would be 0. And this is not what we want. We won't be able to move away. Another thing is that if we look at these filters, this is a visualization of the first layer convolution in a trained neural network. And there are 64 different filters here. And as you can see, each one of them is different from the other. How do we get this variance, these different filters? If we started all the filters by the same value, in the same way, the gradients would be the same for all the filters. There will be no tiebreaker. They will all converge to the same filter. Therefore, we want to start from something that is non-zero and random. So each filter will have its own direction, and the optimization process will steer it in different directions and will have more varied representation. Yeah.
But the gradient is also dependent on the input, right?
Yes.
So,
but if I initialize all the weights to the same value, non-zero, and I have the same input, the gradient will be the same for all the filters. So all the filters will move in the same directions. But now that I have different values,
but you don't have the same input for each.
I have an image, training image, and I have filters here. They are all parameters of the first layer. And I want the gradient with respect to this one to be in different directions. Otherwise, if they are all the same, the gradient will be the same, and they will all move together. It's not something that we want. So we want, yeah.
So then should we always make sure that we have like only unique initializations?
So we start with random, and if you sample randomly the weights, then the chances the two filters would be identical is 0. So it's not something that you actually check, but theoretically there is a non-zero probability that it could happen, but not really.
This and what your precision is.
I have a question. In the first exercise in the course, when we initialize everything to 0, it was better than initial.
Okay, so let's see what happens if we initialize with random. But initializing
It didn't get
stuck.
to 0. So I
Um,
don't understand why.
Okay.
it's the same.
So I need to see what happened there, because if you initialize everything strictly to 0, then theoretically the gradient should be 0 with respect. No, actually, no.
You still have the bias, right?
You have the biases, but no, the gradient with respect to the weights is the input. So so you have a gradient, but it would be always the same direction. It's yeah. So you have a gradient because for the weights, it will make it difficult for the next layers, I think, to move, but it can be done. But again, all the weights, all the filters you have would be the same. Okay, so
It wasn't a neural network. We did a softmax classifier in the first exercise, so it's not the same.
Oh. Okay, so then you don't have filters, you have like all the weights and you learn for each input. Yeah. Okay.
And then the inputs are different, and that's why. Yes. Because the inputs are different in.
Yes.
Okay.
Okay. So let's focus on this random initialization. So we have, let's think about a toy example. We have a multi-layer perceptron, 6 layers. The hidden dimension is 4,000. And for starters, we start with no activation. So it's a fully linear network. It's not very useful, as Asaf taught you, because it can be collapsed into a single layer. But it's very instructive to look at it. So we'll initialize our weights with very small random noise. So we want the type ratio. We don't want everyone to start with 0, but we don't want to assume anything. We make very small noise. Now, remember that the gradients for the weights depends on the scale of the activation. So the activations are the updates for the weights. So we want them to scale well. So let's assume the inputs for this neural network are distributed normal 0, 1. And we want to see what is the distribution of the activation after each and every one of these layers. So after the first layer, we have this nice distribution. Wow, I don't see the letters. So it's roughly 0 mean, and the variance is no longer 1, it's 1.28. We're getting slightly bigger. But as we go deeper and deeper into the network, what happens to the variance of the activations? It grows because the histogram here becomes flatter. So we have bigger and bigger variance. I crop the histogram here so it won't clutter the whiteboard. So if the activations are growing, what would happen to the gradients? They will also grow. So the parameters of the last layer will have very strong gradients, while the parameters of the first layer will have very small gradients. So it's what we saw here. The problem that Adam was trying to solve, we see it here. So if we do not control the distribution of the activation, we have very bad scaling problem for the gradients. And if we continue, we have exploding gradients. So if we have more layers, eventually we'll have gradients so large that we won't be able to do a stochastic gradient descent. So probably even this tiny number is too big for our settings. Let's try something even smaller. What happens if we half the value?
What's the equation for why the variance should increase as we go through the layers?
So we'll do the math in a second and you'll see it, okay? So if we decrease the distribution of the weights, then the distribution of the activations, what happens to it now? It shrinks, the variance shrinks, so we have vanishing gradients. So eventually we have almost zero activations and the gradients are zero. So we have very large steps at the beginning, but the deeper layer don't change. We don't train them effectively. So what happens here? And let's do the math. So a linear layer is input times the weights, and we initialize them with random variables, and we assume the inputs also are randomly distributed 0, 1. So if we look at the variance of the outputs, it equals the variance of W times X. And we can write this matrix multiplication explicitly. And if we assume that W and X are independent of each other and they are all zero mean, this translates into this so the sum becomes just the variance of the single element. And we can break it into multiplication of the variances of the weights times the variances of the inputs. Okay, so we have some assumptions here about the distribution, but these are relatively relaxed. And so the variance of the input is 1, because this is what we assume. And we want to set the variance of the weights such that the variance of the Y would be the same as the variance of X, because we want to preserve the variance through the layers. And this would give us that we actually need to set the variance according to the dimension of the layer. So it's not arbitrary, it depends on the layer. And if we set the variance to this value that miraculously happens to be between 0.01 and 0.02 that we tried before, then we see that we actually managed to control the variance of the activations through the layers. And now we have the same scale of updates throughout the layers. And this entails more robust and easier to optimize neural network. But aren't we forgetting something?
There is no activation.
Right. What would happen if we use a ReLU activation? So a ReLU activation would actually make the distribution look like this, because we zero out all the negative part. And now if we use the same initialization and a ReLU activation, we again hit this vanishing gradient problem. But luckily for us, people have done this math for us in presence of the ReLU activation. And in that case, we need only to modify slightly the variance of the initialization. And with this initialization, we actually have, again, a robust scaling of the activations. Okay? Great. So the starting point is crucial, because if we start at a bad point, we have bad scaling of the activations. We are actually in a place where it's very difficult to get to these local basins of retractions. The initialization depends on the architecture. We need to know what kind of layer, what kind of activation we are using, what is the dimensions of the different layers, and so on and so forth. Luckily, the computation for most popular layers and activations was already done for us, and you can find the functionality. It's called caviar initialization or timing activations or all kind of these special names. And we saw it for fully connected layers, but it can be easily extended to convolution layers as well. And we also had an assumption that the inputs are normalized 0, 1. And images are not usually normalized 0, 1, but we can normalize them. We can subtract mean for all the pixels, and we can divide by some a scaling factor and make them roughly, each individual pixel, roughly normalized 0, 1. And this is always good for training neural network, that the inputs are normalized. Let's take a break for 10 minutes, and we'll be back at 15 plus. Okay, so we talked about details of stochastic gradient descent, different momentum, different optimizers, how to initialize. Let's move on to other subjects, how to control the optimization and the function that we get. So what can go wrong when we optimize? So we are looking for a function. So in deep learning, in machine learning, we have examples, and we want to find a function that actually performs well on these examples. So think about the space of all possible functions in the universe. We don't really have access to this space. We don't really know how to work with it, but somewhere in this space, there's this ideal function that actually performs perfectly on all the examples we have in train, in test, in whatever future example that will be. This is like the ideal function that we want to find. It's not very accessible. We don't really have way to reason about it, but it's somewhere there. Within the space of all possible functions, we can think about the space of all deep neural networks, all the combinations of all the layers, of all the parameters, of all the number of channels. Again, this is a huge space. It's smaller than all possible functions, but still it's huge, and really we can work with this one. What we can do is we can decide on a specific architecture. This is what we do. We design an architecture. We decide on the number of layers, what kind of activations, how many channels, and so on and so forth. Within this specific architecture, within this specific space, it's still a very large space. This space is parameterized by what? No, by the weights of biases of what? Of the model that we have. Yes, so this is the theta. So choosing different thetas will give us different points in this blue space. So within this space that we are working on, so we committed ourselves to this subspace of all possible functions. Somewhere here, there's the best parameters we can find. There's some theta, some instance of this neural network that actually is the closest that we can get to this ideal function. And we want to find this one. But we don't have access to this ideal function because we don't have all the examples that can ever be. We only have the training samples. We hope the training samples are good enough. They represent well the world, but as we saw, there might be some discrepancies between them. So it's not really possible to find this ideal function. We can find something that is work best on our training examples. Do we have any guarantee that we find this set of parameters? Well, no, because we don't have any guarantees about the way stochastic gradient work. We can only achieve this is actually what we end up with. This theta optimization. This is the theta that we got after we tried different kind of momentums, different initial points. This is the best we could do in the limited resources we have. And as you can see, there's quite a gap between the ideal function we are looking for and what we end up eventually. And we can divide this gap to sections. So the first gap between the ideal function and what we actually, the best thing we hope to achieve is the approximation error. Because we approximate the space of all possible functions, this abstract space with a specific neural network, we have an approximation error. We can't hope to get the ideal function. The gap between the best thing we can do with our neural network and what we can, the best thing we can achieve using the training set is the estimation or the generalization error. Because we have discrepancies between the train set and the test set, it incurs an error. Because we only use the training set and we try to do the best for the training set. And if the training set is not ideal, there is a gap. And eventually we have an optimization error because we use stochastic gradient descent. We're not guaranteed to get to the global optimum. There is an optimization error. So what can we do to make these errors as small as possible? So if we have large approximation error, if we are using a function that is not expressive enough, so we are trying to solve computer vision with a single layer, one neuron perceptron, it's going to be very difficult. So we need to change the architecture. We need to make this space bigger, or maybe move this space, try different architectures. If our optimization process is not converging well, this is what we saw in the first part of the talk. We need to tweak the hyperparameters. We maybe need to switch from SGD to Adam. Maybe we need to change the learning rate or add learning rate decays, initialize the weights in different manners. And this is the optimization process. And if we have a gap between the test distribution and the training distribution, what can we do? Ideally, we add more examples. We make these two sets closer to each other, but we don't always, it's not always possible. Training examples don't come by easily usually. You need to annotate them, you need to collect them. It's difficult. So
we saw in the first class that the optimization error is not always a bit, sometimes it's a feature.
it depends on the direction. Maybe it takes you closer to the
To the world.
yes. So this is what we saw in the first part, where you have this kind of loss function. So you didn't get here. This is an optimization error. You got here, but this point is more stable. So in terms of the true error that we don't have access to, maybe this point is better. This function is better. So yes, optimization.
So we don't always want to fix them.
Yeah. It depends. So if you're in a competition, you have a specific set, then you try to squeeze what you want. But if you don't have, if you develop some product and you don't know what the test set is going to be, you have some test set, some validation set just to make sure that you're doing well. I think you would want your model to be robust. But again, it's difficult to measure this, but it really depends. So how do we know what kind of error we have? So the most straightforward thing is to look at how the loss function behaves over iteration of the training process. As we saw before, at each step, we have a forward pass where we estimate the loss and the backward pass where we estimate the gradient. So we have an estimate of the loss function for each and every one of the steps. And ideally, how would this look like? It would go down, yes. So we start with very high loss because we are at a random initial point. And as we progress, we make the model better. Both the training error, we actually moving in the step of the training error decreasing. And we hope that the test error would also go down accordingly. So there is a difference, there is a gap between the test and train because they're usually not identical. But in a good training regime, the trend is the same. Okay? So we have some test sets, some examples that we set aside. We do not compute gradient. We do not optimize the weights based on the test set. We only use it to evaluate where we are. So every once in a while, we check the point that we are at and estimate the test loss. And what you usually see is this kind of behavior. So the training loss decreases all the time because we actively decrease it. We actively take gradient steps in that direction. But at some point, the test loss start to go up. What happened here? Overfitting, yes. What does it mean to overfit? So if we have this simple classification problem, we want to find some kind of separation between the two examples. So we want this kind of separator. It's not perfect. We see that it misses one of the training samples, but it does quite well. And we can expect this kind of separator to generalize well to the test set. But as we train, as we continue to train, what happens is learn this kind of separator. So we put more emphasis on the training set. The model memorizes the training. And now, as you can see, the training error now is much better. It's perfect. But yes, but variance, you can expect this kind of separator not to perform well on new examples because it overfit, it memorized the training samples. And this is what is going on here. So in the first part, we learned this nice separator, but at some point, we overfit to the training examples. Charles, we know? Okay. And once we start memorizing, the training is better because we're memorizing the examples, but it doesn't generalize well to other examples. This is the gap between the ideal point in the training set and the actual point that correspond to the training examples that we have. Just a side note that the losses will always not look this smooth because we have estimates based on on a small batch. So if you look at the curves in weights and biases or whatever other platform you're using, you'll see this, they wiggle a lot, but we follow the trend of this graph. So what can we do to avoid overfitting, to avoid memorizing the training samples? One simple thing is that we add regularization. So we have the cross entropy loss, but we add some regularization on the weights. We want the weights to have small norms. So it will be very difficult for the model to learn these very complex bounding planes. So the model has to find a solution that also has small norm. It's like an Occam's razor. we want the solution to be simple. And how we say simple, we say, okay, it should be small norm. So if we take this norm to be L2, then the vector will be small. If we take this P to be 1, then it usually incurs sparseness. So use as few parameters as possible to find the solution. This is one way of making the solution more simple and avoid overfitting, avoiding these memorizing the training samples. Another thing we can do is we can have more examples. We can increase the training set. But again, we don't want to find new samples and label them. This is very exhaustive. We can do augmentations. So think about it. This is one sample that we have. We have an image and we have a label that says dog. And this is one training sample that we have. What happened if we flip the image? Just simple mirror flipping of the image. It's still a dog, right? But in terms of the values of the pixels, it's completely different. So from the perspective of a neural network, this is a completely new example. It lies in a very different place in the space of all input images. But it comes to us as for free. And we can think of other such transformations. So if we rotate the image a bit, if we change the contrast or we add small noise, all these kind of transformations generate new samples. And we know the label for these samples. It's all dog. And it's basically almost free for us. So the computation of this transformation is very, very light compared to a neural network. And we have more examples now. It would be much more difficult for the network to memorize this specific configuration of pixels to say this is a dog. Because now it needs to learn something that is more conceptual, that is common to all these and hopefully to many other samples of dog, and it would be more difficult for the network to overfit. So we don't have to annotate or acquire new samples. We can increase the training set simply by introducing these augmentations. And again, we don't need to implement them from scratch. Since they are very popular and very useful, there are libraries that do it for us. So there's Torch Vision transformation. There's other packages like Augmentation. They have many kinds of transformations that can be used. So we want to make it difficult for the network to memorize the inputs. We want to have more samples or regularization on the weights. We can think about more ways of making the training hard for the network in order for it to generalize better. Another way is to do a dropout. So if we have this simple network, we have many paths that leads from the input to the output. It can go through many paths through the hidden layers. What we can do is we can stochastically drop path during training. So think about it that at some iteration, we shut down some of the neurons. And at different iteration, we'll shut down others. It will have, it will force the network to learn different combinations of paths for the same solution. There will be some redundancy in the network, but this redundancy will force it to learn something that is more generalizable and more robust to changes in the input and in the architecture. So if we saw that we can introduce noise and variance to the inputs, dropout is a way of introducing noise into the network itself. Another thing we can do is we can, okay, so we look at the graphs. This is where overfitting starts. If we save the weights in intervals, we can simply go to the weights here and say, okay, I don't care about whatever we trained here. These are not good for us. I'll take this one. And this is called early stopping.
That the early stopping of loss should be similar to the eventually to the test loss, like the validation, let's call it validation loss.
Okay, so if you want to be strict, and you want to be strict, then you have to have, and you want to use early stopping, you need to have 3 sets of examples. You have the train set. This is the examples you're using for optimizing for gradients and whatever. You have a validation set. Again, different sets of examples. They should be mutually exclusive. And using the validation set, you compute this validation loss. And you use the validation set to determine at what point you do the early stopping. So this is used for deciding on the early stopping. And then you have a test set, a third one, and you report the result on this one. This is like the way you should.
So my question is about the validation loss and the test loss. What can be the root cause for different loss? Like
Okay, so what's the different? Why there's a different loss on the training and the validation?
no, validation is used for where to store.
But it's again, you have 1 million images for ImageNet. They were all curated the same, and yes, okay. So despite the fact that all these images were collected together and were tagged by the same people, if you look at different sets, different splits, you'll have slightly different values for the validation and for the test set, for the test error, because they are not the same images. And the network has some variance. So ideally, if all the images were collected together from the same pool, were annotated by the same people, then the difference between them will be that big. And again, if you try to beat everyone on ImageNet, then you really care about these small differences, but that's a different story.
The validation test, predict the test.
They all predict the test loss. And the test loss is not always what you want. So if you develop a product, you care about what the prediction would be for images that the user would upload in a month. And I don't know what's going on there. But this is a way of estimating and saying, okay, we are assuming that this is the distribution that we work in, this is the world we live in, then we reasonably well represented by the validation of the test. And it's important that they would be different. Otherwise, if you optimize on the test set, you will overfit, and the results you get won't reflect the true abilities of the network to generalize. So this is why you need to have distinct sets if you want to use early stop. Okay? Okay, so let's recap what we saw so far. So we have a very large space of solutions, and we want to be as close as possible to the ideal function that we search for. If we have bad architecture, we have large approximation error. If the training set and the test set are quite different, then we'll have generalization error. If we overfit, if we memorize the training set, we'll have large generalization error. And we have ways to tune the optimization process to be as close as possible to the best estimates we have given the training set. Okay? And we saw both from the Adam optimizer and the way we initialize weights that actually the scaling of the weights and the scaling of the inputs plays a crucial role in the ability of the stochastic gradient descent process to converge well, for the steps to be relatively uniform for all the parameters and for the gradients to behave well. So normalizing the weights and the inputs, the activations, is very important. And one way of doing this is using normalization layers. So let's think about what happens if we don't do any normalization. We have three layers. We have the inputs that are 0-1 normal distribution. And as we saw before, if we don't pay really close attention to how the weights in this layer are initialized, then we'll have a distribution shift of the activation. We'll have slightly different distribution of the weights. So if we have some biases here or whatever, and again, if we move forward in the deeper in the network, this distribution of activation may change, and this affects the size, the magnitude of the gradients, and how the optimization goes. And suppose we want the loss function, the regularization we have on the weights, on the activation, we want to have these nice zero mean one variance behavior. So when we do backward, we try to correct the weights such that they will shift the distribution according to what we expect. So after the backward process, we update the weights such that it will take this input distribution and it will map it to something that behaves better, more zero mean unit variance. And we do it for all the layers in the backward process. So we update the weights such that they will map the inputs to something that is more well behaved. But now that we changed the distribution of the inputs for this layer, what would happen here? So we updated the weights. So we had a forward and a single backward step. What would happen now? So we updated the weights for the last layer based on the gray distribution on the inputs. But after we updated the weights of the second layer, the gray inputs, the gray distribution is no longer valid. We have this bluish. So actually it means that we overcompensated in the update of the weights. So we are actually moving the rug under our feet. So when we update the last layer, we always look at the forward distribution of the activations, of the input activations. But whenever we update the weights of shallower layer, this distribution shifts. So basically, we can't start updating the weights here seriously before all the previous layers converge to something that is stable. Otherwise, we keep messing around. So instead of training all the layers simultaneously, what we actually do is we train the deeper layer, the first layers at the beginning of the process, and only when they converge, we actually make significant and meaningful steps for the deeper layer. This entails a very long training and a very unstable one, because the loss function only sees the last layer, and this one is very unstable. So what can we do to prevent this? And as the titles say, we want to do normalization. So the first invention of normalization was the batch norm normalization, I think 2015, something like that. And it basically adds a batch norm layer after the computation layer. So we have a linear layer or convolution layer, and then we add a batch norm layer. And what this batch norm layer does, in the forward pass, it normalizes the activations. So we have some nice activations at the input to the original layer. The layer shift the distribution towards something that we don't like, but the batch norm layer can compute the mean and variance of this distribution and renormalize the weights in the forward pass. So what we get after applying the layer and the batch norm, we have weights that, activations that well behave. And this is done in the forward pass. And so we add batch norm for all the other layers. And in the forward pass, we maintain the nice distribution of the activations. So there's still computation going on in this layer. They are still mixing and shuffling the activation, the weights. They're doing the learning. But the batch norm makes sure that this learning stays well behaved. And now, when we compute the update in the backward, all the weights are normalized, all the layers are updated at the same rate at the same time. So the process is simultaneous, it's much more efficient, and it's much more stable. Yes?
Doesn't this invalidate what we talked before about the initialization?
It doesn't invalidate, it makes you much more robust to the initialization. So now you care much less. Yes. So I think if you still do like crazy initialization, you can break it, but it would be much more difficult. And again, this is 2015. I think you had the architecture tutorial. No, not yet. So once you have these normalization layers, you can start training very deep network, very large architecture. Until then, it was very, very difficult to train deep networks. You had to be very, very specific about how you initialize the learning rate. This really made a change.
How does the backpropagation go to the batch normalization?
It's not a problem. It does what it does. So we see this mathematically. So we have an input. We estimate the mean and the variance. And these are constant. You don't need to do to differentiate through them. And you have learnable parameters for the normalization layer, again, for historic reasons. And you output the normalized output. So you subtract the mean, divide the variance, plus some constant to make it stable, and then you scale. But you can differentiate this expression quite easily. So you treat mu and sigma as constants, and you differentiate. You compute gradients with respect to gamma and beta. Okay? So this is during training, where you have a mini batch and you can estimate the mean and the variance on the batch. But what do we do at test time? Test time, we don't have a batch. We don't have a collection of examples. We might have only a single example. So how do we estimate the mean and the variance at test time? So what we actually do is at training time, we keep track of the mean and variance. So we have a mean and variance that are characteristic of the training set. So these are the mean activations for all the images in the world. And we update them through the training process because these mean and variance in deeper layer depends on the activation on the learning weights that we learn. But eventually, we use this exponential moving average scheme. We have good estimates of the mean and the variance. So during training, we estimate mean and variance and keep track of the parameters, and we update. And at test time, we can use these parameters that we estimated. Okay? And think about it. This batch norm layer stores mean and variance parameters and this gamma and beta scaling and bias parameters. These parameters are updated in a conventional way in the backward process through gradients, but the mean and variance, they don't see gradients. They are updated in the forward pass by accumulating the statistics. Okay? And in test time, yeah, we simply output the y based on the accumulated mean and variance. And for convolutional neural networks, this looks like this. So the input is batch size, channels, and the spatial dimensions. And we estimated mean and variance for each and one of the channels. So we have a channel mean for this layer. And again, we learn these bias and scale for each channel. And for some people, this visualization helps. So we have the batch dimension, we have the channel dimension and the spatial dimension, and we actually normalize according all these loop points together. Okay? Great. And now we have the architecture, we have convolution layer, we have activation. Where do we want to place the batch normalization layer? After the convolution or after the activation? What? Why after the activation? Okay, and
I say just before the value, so it will be active around the 0, 1.
yes, because if your activation zeroes out the negative part and you normalize everything to be zero mean, then it's a bit problematic to do it after the value. So usually they are placed right after the linear layers or the convolution or the fully connected and before the activation. Okay, but yeah. So batch normals makes the training very robust to initialization. It allows training for deeper neural networks. It allows for higher learning rates because everything scales now in the same manner, roughly. And this is very good news for training big models. The downside is that it has different behavior at train and test, because at training, we estimate the mean and variance based on the batch. And at test time, we use the accumulated statistics. This can be annoying sometimes. So we can do other kind of normalization. So we can think about normalizing using layer norm. So now, instead of computing normalization for each channel, we can compute something that is for each and every instance in the batch. So if you look at it visually, this is the batch norm, and this is an instance norm. So it computes a normalization for each layer, for each and every element in the batch. And then we don't care about the batch anymore. We can do it for every sample, even at test time. And we have the same behavior for train and test. And since normalization is so good, there are many flavors of it. So we can have instance normalization that does the normalization per channel. So think about it like a contrast enhancement for each and every channel in the sample. And some applications, some domains prefer to use one normalization over the other, but basically they all started from the batch norm and made training much easier. Okay, so this is for today. What we learned today is actually that training neural network has a lot of details that we need to pay attention to. So just writing down a nice neural network in PyTorch and throwing at it all the examples won't always get us a good model. So we need to pay attention to the way that we optimize the parameters, how we search in this huge space. But there are many tricks that make this search much more robust. So we use Adam that scales differently for the variance according to the variance in each one of the parameters. We have regularization that help us avoid overfitting and find solutions that generalizes better to the test examples. And we have normalization layers that help us govern the behavior of the activation through the training process and ensure a more stable and smooth training process. On Wednesday, you have a tutorial with Rafael on CNN architectures, and you'll actually see how these landmark architectures evolved over time. And next week, Tali will present her talk about visualizations and understanding of neural networks. So we learned something, we have nice test error, but we want to know what this network learned. So Tali will talk about it. Thank you very much.
Well,